The last set of notes for Calc BC, areas of regions defined by polar graphs. So in the last one, we saw how to graph polar functions and how to go back and forth between polar and Cartesian or rectangular, and how to find the slope of a tangent line or the derivative of a polar function. Now, in AP Calc BC, we do not get into second derivatives of polar graphs. We do not get into lengths of polar graphs. But what we do get into is areas of polar graphs. So let's talk about what it means. All right. So here I'm going to just draw a sketch of a polar function. So I'll say this is some function, some polar function, all right? R of theta. Now, when we talk about the area under a curve from A to B, we're talking about this. When we're talking about an area contained within a polar function, since in a regular function, x is the independent variable, A to B represents a distance along the x-axis. But in polar, theta is the independent variable. So theta represents a change in angle as you go from 0 to 2 pi. So one way to think about this is the limits of A and B here represent x values. The limits on theta are angles alpha and beta. So let's say I've got the angle. I'll use a ruler to make it look nice here. This is the angle alpha. So this is theta equals alpha. And then let me draw in the angle beta. There's the angle beta. Theta, we'll call that theta 1 and theta 2. That's the angle beta. The area contained within that region is the area we're talking about. So the area of a polar graph is an angle contained between the origin, let me use a different color, the angle contained between the origin and the function from one angle to another. So this right here is the area within a polar graph from alpha to beta. All right, so let's talk about where does this formula come from that you see right here. All right, well, obviously this is, some finite angle here, beta minus alpha. What we're going to do, just like we did with rectangles and areas in the Cartesian or rectangular coordinates, is we're going to take that down to an infinitesimally small little piece. So imagine that I just take a very small snapshot of this function. I just take this, maybe this little part just right, whoa, that's way big. This little part, like right here, just that little piece right there. All right. So I'm kind of zooming in on it. So when I zoom in on that little piece, what I'm going to see, if I zoom in close enough, is something that is effectively just a straight line. Sorry, my pens are too thick here. It's effectively just a straight line, because that's part of a, when you zoom in far enough and far enough, you get what is essentially just a straight line. Now let's think about the origins over here somewhere. So I've got just this little sliver right here. And the radius on either side is going to be different. Obviously, the radius here is different than the radius there. But if I bring these two angles really close together, in fact, instead of theta, if I make this an infinitely small little strip d theta, these two r values will be effectively the same, because the radius is almost exactly the same if you're right next to another point like that. Now, there's a known formula for the area of a triangle, because that looks like a triangle, right? Even this looks like almost like a triangle. The closer alpha and beta are together, the more this is just a triangle. Well, we know there's a commonly known area of a triangle, which is 1/2 r squared sine of the angle in between. Well, in this case, that is 1/2 r squared sine of d theta. Now, it is easily shown, I'm not going to go through it here, but it's easily shown, and you could take out a calculator and figure this out, that the sine of an angle theta is very close to theta when theta is very near to 0. And I just pop one out here for you, and you'll see. Come on, turn on, calculator. There we go. Watch this. Pick an angle that's really close to 0. 0.01. Do you see that the sine value you get is very close to being that actual angle? Go even closer to 0. 9.99999 times 10 to the negative fourth, that is 0.01 effectively. So the sine of an angle is very close to the angle's same value when theta is approximately 0. Now we're talking about, infinitesimally small. So when you're infinitesimally small, the sine of d theta is going to effectively just be the same as d theta. So you end up with 1/2 r squared sine d theta. Now, that's the area of this little sliver. And remember, this sliver I'm talking about, going back to this picture, that sliver fits in pretty much like this. It's an infinitesimally thin little sliver. I want the area all the way to cross. So what I'm going to do is the same thing we do with rectangles, is I'm going to use an integral to add up all these little slivers together across here to get the full area. And that's what the integral does. So that's where this formula comes from. So the area contained within a polar function can be found by integrating 1/2 r squared d theta. So just to clean it up a little bit, here's my polar function. If I want the area from alpha up to beta, we're talking about this area right here. I can find that by integrating the r function squared, half of that, with respect to theta from alpha to beta. So let me go through an example of how you might use this. Generally, you are going to have a calculator to do this. So I want to look at the area inside the curve, r equals 3 cosine 3 theta from 0 to pi. So why don't we just go ahead and graph this function. So hit the y equals button. I'm already in polar mode. 3 cosine 3 theta. I'm going to set my window to go from 0 to pi, which it already does. Hit the graph button, see what we get. Okay. Now, this is where it's really important to, again, pay attention, because let me go to my window. I designated you here from 0 to pi, but let's say I hadn't done that. You'd have to figure out what the correct interval is. And I watch what happens when I do this to 2 pi. You see how it's still working? You saw that up there? If not, rewind the video, you'll see it. It's repeating itself. And the problem with repeating itself is if I want the area, if I integrated this from 0 to 2 pi, I'd get these areas all twice. And I don't want that. I only want them once. So really what my goal is to get the region over an interval that graphs it one time only. So 0 to pi, graph, and not working anymore. So I can just go ahead and do this. Now I have the right interval. So area is 1/2 integral from 0 up to pi r squared d theta. So in this case, that would be 9 over 2 integral from 0 to pi of cosine squared 3 theta d theta. So I'm just going to go ahead and do this one on the calculator. So let's bring it up. So I've got 9/2. Oops, wrong button. 9/2 math 9 integral from 0 up to pi of cosine of 3x. And it's putting thetas because I'm in radian mode. I'm in polar mode, which is totally fine. That doesn't matter. Integral with respect to theta. Even if I was in function mode and I was typing in x's, it would be exactly the same thing. So that should be good. Hit enter. And we're going to get, what is that, 7.0685. 7.0685. All right. Number 2, find an integral that will give the area inside the smaller loop of the limmason, r is equal to 2 cosine theta plus 1, then use a calculator to evaluate. All right, so I already know what I'm going to use. I'm going to use 1/2 integral r squared d theta. The question is, what are the limits going to be? And here's where I'm going to use a calculator to explore this and figure it out. I want the smaller loop. So I need to figure out what gives me the smaller loop. So let's just look at this thing. Notice that they haven't given me any indication here as to what theta limits I should be using. 2 cosine theta plus 1. All right, I'm just going to go to a standard window. All right, let's zoom in. All right. Now, what you should be looking at, and let me turn it back off and turn it back on again so you can watch it. When I hit graph, look at it graphing and then look at the little working symbol up here. We want essentially the graph to fully complete and the working symbol to stop at the same time. And you see that happens. What that tells me is 0 to 2 pi graphs the entire thing. The problem is I don't want an area contained within the entire thing. I only want the area within the smaller loop. So I need to figure out what values of theta are going to make that happen. So I'm going to work this out by hand just to show you. Now, what you could do is you could just go in your window and you could start, just choosing different theta values. Like you might say, oh, will pi over 4 to pi do it? You could guess and graph and see what happens. No, that obviously doesn't give me what I want. So I have to figure out something different. But what I want you to notice here is that when the defining angles that start that inner loop and end that inner loop happen at the pole, they happen at the origin. In other words, they happen when r is equal to 0. So I'm going to work this out by hand right here just to show you how I can do that. If I set r equal to 0, I will be able to find the values of theta that that take the graph to the pole, to the origin. So, here, let me be careful about this. 2 cosine theta plus 1 is 0. So 2 cosine theta is -1. So cosine of theta is -1/2. Now, using your knowledge of the unit circle, you should be able to work out that the places where theta is equal to -1/2, where cosine of theta is equal to 1/2, -1/2 is when theta is at pi over 3. No, 2 pi over 3 and 4 pi over 3. Let's go back to the calculator. Let's use those as the window limits on theta. 2 pi over 3, 4 pi over 3. Now, if I did this correctly, we should only see the inner loop. There it is. Those are the limits I want to use on my integral. So I'm going to go from 2 pi over 3 up to 4 pi over 3. And I'm just going to type that right in the calculator. Now I've got the function in as R1, so I can just go like this. Math 9 integral from 2 pi over 3 up to 4 pi over 3 alpha trace R1 squared. Integral with respect to theta. Just don't forget the 1/2 at the end. I should have put it on first. Divide by 2. And I get 0.5435.